This is Cycle 1, Lesson 3 of Advanced Functions, MHF4U1. Today we're looking at characteristics of polynomial functions. There's a whole lot of information in this lesson. Again, being just a video lesson, I'm going to try to get through things quickly. There's a lot of information that you can just read. I'm not going to read it all to you. You'll see as you go through the note there's a lot of text which I will just hit the highlights of, and then you can read it for yourself for more details. But I will do the examples and, again, try to emphasize the highlights. So the first thing, we're going to look at groups of polynomial functions so that we can see what patterns are going on with them. So the first group we're going to look at is this group of 3 that's on the left side of my screen, our screen here, y equals x cubed, y equals x cubed plus x squared minus 4x minus 4, and so on, those 3 there. So what we want to do is we want to see what those graphs look like. So I've got them typed into Desmos already to save a little time. So here's the graph of y equals x cubed. That's the parent function for a cubic. It's got that sort of swooping shape to it. That's what I'm always going to refer to that as a swoop, because that's what I think of. So that's the first equation in that grouping. Here's the second equation. I'll just turn it on. So the blue one is the second equation. As you can see, I can toggle things on or off on Desmos. So I've toggled on the second equation, which is now the blue graph, and you can see that it's got some similarities, right? As far as the end behavior goes, it looks like it's the same going from quadrant 3 to quadrant 1, and but it does have a bit more going on with it. Let's take a look at the third one, the final one from this group. That one's in green. Also, some similarities. Shape is kind of the same, end behavior is definitely the same, quadrant 3 to quadrant 1, but it's moved around a little bit. All right, so try to keep that in mind a little bit as we go back and then look at what goes in this table. These are all degree 3, meaning that the highest exponent for every one of these is 3. And the end behavior, as I pointed out, for every one of them goes from quadrant 3 to quadrant 1. Now, here's something that we haven't talked about yet. Number of local maximum points and number of local minimum points. Actually, I'm not going to differentiate between local and absolute. I'm just going to look at the total number of max and min points. So let's go back and look at this graph here. Let's take a look at the green, the blue one, maybe easiest to see. This blue graph has got a local maximum that I've just highlighted here at negative 1.5, etc., and 0.88-ish. It's also got a local minimum for this one I just highlighted at 0.87 and negative 6.1. So that's what a local, it's not the absolute maximum or absolute minimum, because the graph continues to go up beyond those in a different part of the graph. It continues to go down in a different part, but it does have those two, that one local maximum, that one local minimum. We call those turning points as well. So it's got 2 turning points. So that's what this next column is looking for. So it's got that blue one that we had this equation here. That graph was in blue. It's got 2 turning points, as I just pointed out. If we go back and look at the other 2 and count up the turning points on it, well, the red one has no turning points, does it? It doesn't actually go back down. It's always either going up or going horizontal. Right at the origin, it's actually going perfectly horizontally. But it never goes back down and then up again. So it doesn't have that same feature as number 2 and 3 have. And the third one also has 2 turning points on it. So that's what goes into this part of the table here. So the first one, no turning points. The second and third one each have 2 turning points. And then the number of x-intercepts. So you can see that we've got 1, 3, and 2 going on here. Again, let's just see what's going on. We got one x-intercept for this one. We've got 3 x-intercepts for this blue one. And we have 2 x-intercepts for this green one. So we got 1, 2, and 3. So that's what we had for that first group. Okay? So that's the first row of the table. The second row of the table is another group of polynomials, and all that's happened is all the signs have been changed in all of these. So I didn't type them all in again, but let's just go through and change all the signs on these. So for the first one, well, you can see I'm going to change this from a x cubed to a negative x cubed and see what happened there. It's reflected in the x-axis, right? Let's change this one, change all the signs here, make that negative, negative, positive, and positive. Turn it on, and it looks like something's happened with this one where it's also sort of been reflected. And this last one, let's change the signs on that. And turn it on, and again, basically they've all been reflected in the x-axis compared to the way they were. So now they're all going from quadrant 2 to quadrant 4 as far as their end behavior goes. They're still all degree 3. We can tell that from looking at the equations. They all go from quadrant 2 to quadrant 4 as we're reading it from left to right. The number of maximum and minimum points, in other words, the number of turning points is still 0, 2, 2, because all I did is reflect them all, and the number of x-intercepts is still 1, 3, 2. So that is that group. And the next group, y equals x to the 5, and so on. There's 3 more that go with it. Let me turn these off, and let's see what they look like. Here's y equals x to the 5. Very similar to y equals x cubed. Slightly different shape. Oops, let's get rid of that negative so we can compare them. See, they're very similar, right? Red one is y equals x cubed, purple one is y equals x to the 5. Really similar because they're both odd degree functions. We've talked about that a little bit as well. But then we got some other degree 5 ones, and there's some weirdness going on with this red one. I don't think we can see the whole graph, so I'm just going to zoom in a bit so we can see more of it. I'm going to turn off there we go. So it's got this weirdness going on where it starts in quadrant 2 at the top left, it goes way down into quadrant 3, comes back up into quadrant 2, crosses into quadrant 1, does a little zigzag at around the point 1 on the x-axis, and then heads down to finish up in quadrant 4. And it looks like it goes on forever into quadrant 4. And so that one does this really roundabout route to get there from quadrant 2 to 4, but it does end up there. Oops. Why is it? Oh, that one's negative. Okay, I see what's going on. So gets to be a bit of a mess if I have them all on here at once. So we've looked at the purple one. Here's the black one. Notice how it's also degree 5 with a positive leading coefficient. You know, spoiler alert, I might as well just talk about it right now. It has to do with, everything has to do with the leading coefficient and whether the degree is odd or even for the function. So these are all odd degree functions, and so the first two have positive leading coefficients, the two that we can see, and so they go from quadrant 3 to quadrant 1. This last one, this red one, is also degree 5, but that negative leading coefficient reflects it in the x-axis and makes it go from quadrant 2 to quadrant 4. So this is what we have filled in for these 3 here. They're all degree 5. We have the end behavior written down. They have, I guess what we should talk about is the number of turning points again, so this third column. So I'm back to looking at this again, number of turning points. And this one has no turning points, no local max or min. This one's got 1, 2, 3, 4 turning points, right? And this one, again, hard to get it all on here. 1, 2, 3 turning points. Nope, 4. My mistake. 4 turning points. So where it changes from going up to going down, or from going down to going back up again. So 0 for that one, 4 for the other ones. Number of x-intercepts, I won't count them for you. You can do that. Hopefully you've got the idea by now. And in fact, going through this took me a little bit of time. You've got the idea of how to do it. So what you need to do now is type in these equations to see what's going on for the even degree functions, and then you can look to see why I've got it filled in, or compare it to what I've got filled in here, so that you can see that it does indeed match. Okay, so here are some of the key features. Like I said, a lot of information in this one. There are a couple of examples, but just to give you the highlights, to recap something that's already come out and maybe point out a few other things. So let's go back. We just finished looking at odd degree functions, and I talked about what's going on with the leading coefficient. Those are the two things you need to put together. Is it is it odd or even, the degree, the highest exponent, and is the leading coefficient positive or negative? And so we're just looking at odd degree now. If it's got a positive leading coefficient, it's always going to go from quadrant 3 to quadrant 1. Zoom in a bit here just to focus on this is what we're looking at. So here's two examples, but any odd degree function will follow this same pattern for end behavior. They will always go from quadrant 3 to quadrant 1. If they're higher degree, like 5 or 7 or 9, they may have more zigzags along the way, but the end behavior, if you go out far enough, is going to go from quadrant 3 to quadrant 1. And if it's got a negative leading coefficient, that's simply reflected in the x-axis, and so it goes from quadrant 2 to quadrant 4. The way I tell people to remember this is just any odd degree function will behave like a linear function. So in these two pictures here, you can see there's a couple of blue lines. On the left-hand one, there's a blue line going up to the right. In the right-hand one, there's a blue line going down to the right. Think of it like negative or positive slopes. And so any odd degree function will behave like something like a linear function with a positive slope if it's got a positive leading coefficient, and a negative slope if it's got a negative leading coefficient. Other things that we saw about the odd degree polynomials is they have at least one x-intercept. Well, the reason why they have at least one x-intercept is because if they're always going from 3 to 1 or quadrant 2 to 4, they have to cross the x-axis. There's no way to get from quadrant 3 to 1 or from 2 to 4 without crossing the x-axis. So it's always got at least one x-intercept, and it can have a maximum of n x-intercepts. What is n? Remember, n is the exponent. It's the degree. So a linear function, degree 1, can have a maximum of one x-intercept. It can only cross in one place. Degree 3, like we can see here, this is a degree 3, can have up to 3 x-intercepts. And this one, this red graph you can see here, does have 3 x-intercepts. It doesn't have to have that many, though, because we saw examples where it had just 2. It depends on where the graph curves and whether it crosses the x-axis again. So it can go from 1 up to n x-intercepts. The domain of all odd degree functions is all real numbers. They go on forever from left to right. The range is all real numbers. It goes down forever and up forever. They have no overall maximum. When it says they have no maximum point or minimum point, they mean no absolute, no overall ones. They can have local ones, but it has no overall maximum or overall minimum. Think of a parabola. A parabola does have an overall maximum or minimum. It's not an odd degree. It's an even degree, but even degree ones can have overall maximums and minimums. Think of the vertex. But there is no vertex for an odd degree function. Okay? Odd degree polynomials may have point symmetry. We'll talk about symmetry later. For even degree functions, what you'll see, if you did what I said to do above with those, doing Desmos on those even degree examples up above, is you'll see that they all behave like parabolas. A parabola, degree 2, is the lowest degree for an even function. You can't have a 0 degree function, so after 0, then we have 1, which is odd, then we have degree 2. Degree 2 is our lowest even degree. That's a parabola. You guys are familiar with that. All even degree functions behave like a parabola. So, in this example here, you can see the blue one is actually degree 2. It is a parabola. The red one is degree 4. It's blurry, but that is degree 4. It's not a parabola, but it's got end behavior that's very similar, right? It opens upward. We can definitely talk about this red graph opening upwards. And so if it's got a positive leading coefficient, think of a parabola with a positive leading coefficient. It opens upwards. So it's going to go from quadrant 2 to quadrant 1. But any even degree function will do that. The range is going to be either, well, if it's opening upwards, it's going to be anything higher than whatever the minimum value is. So if it's a parabola, it's anything higher than the vertex. The range will be anything higher than the vertex. An even degree polynomial with a positive leading coefficient is going to have at least one minimum point. So if they're all behaving like parabolas, they don't go down forever. There's a minimum point beyond which it doesn't go. So it has to have that minimum point. Again, it's the vertex in a parabola or some other absolute minimum if it's a higher degree function. Again, negative leading coefficient just means it's reflected in the x-axis. Now they're all going to behave like parabolas opening down. So that means they're all going to go from quadrant 3 to quadrant 4. And the range is going to be anything that's below the vertex or whatever that local maximum is. There has to be a an absolute maximum. An even degree polynomial with a leading coefficient has to have at least one maximum point. Even degree polynomials may have from 0 to a maximum of n x-intercepts. So as you've learned in the past, you don't have to cross the x-axis with a parabola. It could have its vertex, for example, above the x-axis and open upwards. So there can be 0 x-intercepts for an even degree function. And it can go up to n. Remember, n is the degree. So a parabola can have up to 2 x-intercepts. Degree 4 can have up to 4 x-intercepts because of the path it takes. The domain of all even degree functions is all real numbers. It goes on to the left and to the right forever. Even degree functions may have line symmetry. Parabolas have line symmetry. They have the axis of symmetry. Degree 4 functions may have line symmetry. This red one you can see here does not. It doesn't have an axis of symmetry. It could have an axis of symmetry though. Y equals just x to the 4 would have line symmetry. Key features of graphs of polynomial functions. So this is for all polynomial functions. A polynomial function of degree n, where n is a whole number greater than 1, may have at most n minus 1 local maximum and local minimum points. So again, turning points. So what that's saying is a parabola, that's degree 2, can have up to 1 turning point. And it does, that's the vertex. But cubic, which is degree 3, could have up to 2 turning points. It doesn't have to have that many, but it can have 2 as the maximum. So it can always have 1 less than the degree. Any polynomial function of degree n, the nth differences are equal and constant, or constant, have the same sign as the leading coefficient, are equal to this formula here. We're not going to worry about that now. We're going to come back to that later. We've got enough stuff to worry about for now. All right, we've already talked about, I just talked about the number of local maximum and minimums. what do I want to say here? You can read what it says in white here. The least possible degree refers to the fact that it is possible for the graphs of two polynomial functions of either odd degree or even degree to appear similar. Sometimes they do look very similar, even though one may have a higher degree than the other. For instance, these two graphs here below look really similar. However, this one is actually degree 4, and this one is actually degree 8, even though they look similar. And they have the same x-intercepts, but it's because one of them has a double root and the other one has a quadruple root. And I'm going to talk about double roots and quadruple roots later as well. So just be aware that you can't always tell what degree a function is. So we talk about the least degree. If I just gave someone these two graphs and said, what's the least degree for this would be 4. It couldn't be, and it has to be an even one, right? So I can rule out all the odd ones. It can't be quadratic because that would only have one x-intercept. Sorry, not one x-intercept. It would look like a parabola. This clearly doesn't look like a parabola. It looks like a W. The lowest degree that this could possibly be is degree 4, even though one of them is degree 8. And lastly for today, even versus odd functions. An even degree polynomial function is even if the exponent of each term of the function is even. An even function satisfies the property f at negative x is equal to, blurry again, sorry about that, is equal to f at positive x for all x in the domain of f at x. An even function is symmetric about the x-axis. So again, we'll talk more about this stuff. So if this is getting a little bit or a lot confusing to you, this what I just said, here's what I want you to take away from it for now. An even function is always going to be symmetrical about the y-axis. So this here, imagine that the y-axis, that we folded this graph in half on the y-axis, it's symmetrical. And we're going to call that an even function. So if it's got a line of symmetry, and that line of symmetry is the y-axis, then that's an even function. An odd function is one that, again, you can read what it says here. I think I'll leave that for now, but just to point out what it looks like. An odd function is one that, if I was to rotate it around the origin, so if this was somehow something I could grab a hold of and just spin it around the origin 180 degrees, and it looked exactly the same, that would be an odd function. So we're not talking even degree and odd degree anymore. We're just talking about odd function and even function. So slightly different terminology that means different things. So example, determine the key features of the graph of each polynomial function. Use these features to match each function with its graph. State the number of x-intercepts, etc., etc. All right, so here are a bunch of equations, and I've already got the answers filled in, so I don't want to show those. So here are some equations. I want to match them with the graph. All right, so let's look at the first one. Here's what I'm looking at. This is a degree 3, if I look at that equation, with a positive leading coefficient. So what graph could match degree 3 with a positive leading coefficient? Well, it wouldn't be this one. This one has to be an even function because of the end behavior. This one's also even because of the end behavior. It has to be either the third or the fourth one to be odd degree. To have a positive leading coefficient, those ones always go from quadrant 3 to quadrant 1. So A has to match up with this graph here because of that little bit of detective work we just did. The next one, B, has got an even degree and a negative leading coefficient, so it's like a parabola, opening down. So B would have to match up with this one. This is the only one that's like a parabola in its end behavior and opens down. And let's just go with colors here. Odd degree, negative leading coefficient has to be this one, because that's the one that goes that crosses the x-axis. It has that, it's like the linear behavior or like the behavior of a linear function, but the negative reflects in the x-axis, making it go from 2 to 4. By process of elimination, that means that this one the last one, D, has to be 2, but let's just confirm. It's got an even degree, a positive leading coefficient, so it's like a parabola opening up. Yes, that matches, right? All right, that's it for now.